So today I begin with the first lecture in which I will talk about high harmonic generation in the context of time domain interferometry. Um, Now it's very difficult to speak on this topic because I know that Shiva has already given a number of lectures and so has Vinay, and it's very hard to say anything which either of them may not have said earlier. But I hope that these lectures will be interesting. So let's begin with this. I'll begin with some preliminaries which I'm sure all of you know very well, especially those who have attended lectures on attosecond science earlier. But for the sake of completeness, let me just remind you that light travels through about an angstrom in an attosecond. So it's very fast, and it takes about 150 attoseconds for an electron in the first Bohr orbit to go round in the ground state 1s state. So it's a very short interval of time. Now the electron is of course not quite a particle, which is like the Kepler model of planetary physics. It's not like a point particle which is going round in circles. So this model of 150 seconds is not a very satisfactory one. What you really have are wave functions and superposition of various functions which constitute a wave packet, and what you really have is an electron wave packet which moves from one part of the atom to another part of the atom, and this is what we really want to study. Okay, I mean, just imagine the power it will give you to study chemical reactions, biological processes, if you can watch electron movement of electron wave packets on that time scale. So that is the reason this field is so important, and since this happens in attoseconds, a femtosecond laser pulse is unable to see this. So this is why you really need ultra fast attosecond pulses. So this is the reason that the Nobel Prize 2023 was awarded to Ferenc Krauss, Anna Lewiller and Pierre Agostini for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. So this is part of the reason this field has attracted so much attention in recent months. This is a very recent development, and you have an idea of the time scale, because when you look at a stopwatch you are used to like time intervals of the order of a second. Cameras have shutter speeds of the order of milliseconds, 10 to the minus 3, then fast electronics at operate at nanoseconds, and then you have even quicker physical processes like molecular vibrations, photosynthesis and so on, which get to faster and faster, and then the electron wave packet movements in atoms and molecules takes place over the attosecond time scale. So how do you generate attosecond pulses? And that's a big question which I am going to discuss in the first two lectures. You begin with intense short pulse laser. When it interacts with an atomic gas, means it could be in the infrared laser, then the atoms respond to this laser in a very non-linear fashion. It's extremely non-linear, we will talk about it. And one of the outcomes of this interactions, not the only outcome, but one of the outcomes of this interaction is that higher frequency lasers, which are multiple, the frequencies are multiples of the previous one, but only odd multiples. So if the original is omega, then you get omega plus 2 omega. So you will get omega, 3 omega, then 5 omega, then 7 omega. So those are the ones that you get, which are coherent, and these are the attosecond laser pulses which are generated. And there is a very nice paper by Levenstein et al. I want to draw your attention to the last two authors, Anna Wheeler, who is this year's the last year's Nobel laureate, and Paul Karcam, about whose contributions also I will be talking about in today's two classes. So this whole business is about doing chronophotography, and if you want to take a picture of things happening very fast, you need a device which can register. You need sensors which will operate that fast, which will have very rapid shutter speed. So if you don't have a shutter speed which is fast enough, then you are not going to see the different colors of the blades of this fan that you see in the picture, and depending on whether the shutter speed is medium or really rapid, you will be able to resolve the colors to a different extent. So this technology really began in the 19th century, and there was this question. I mean, people did not know if a horse has all the feet in air at any specific instant of time when it is galloping, and this could not be seen, and you really needed to develop very fast cameras for that. And Edward Muybridge, who writes his name, who spells his name in a very peculiar way, he developed this technology in 1878, and this is where chronophotography really began. And we have come a long way, and now we are looking at speeds at the level of attoseconds. So this is a very short period of time, because if you look at the age of the universe, it is of the order of 10 to the 17 seconds, and this is the inverse of it. So it's a very very rapid process, and this is what we are looking at. The previous major milestone in this was the femtosecond pulses, and the femtosecond is 1,000 times less fast. It's 10 to the minus 15 seconds, and this was also celebrated by a Nobel Prize in 2018. It was awarded to Arthur Ashkin, Morrow and Strickland, and this has already become a very common resource in many technologies, including eye surgery, grabbing bacteria, optical tweezers and so on. So this is very advanced and useful technology. But they were very smart in developing this. It was not very easy to develop even femtosecond pulses. So they used this technique called as the chirped pulse amplification, and basically this is the picture that you have. You have these short pulses which you stretch temporally and spectrally. You stretch them out using this double grating arrangement, and then it is the stretched pulse which you amplify and then recombine, recompress in a inverse similar process. So that is the technique which was used, and this was really a very smart way of doing it. And the reason it was smart is because there was no other way amplification which is required for laser. It could not be achieved because you need a medium in which amplification will take place, and the medium would get destroyed by the energy of the laser. So this way of temporal and spectral stretching out a pulse and then amplifying it and then recombining, recompressing it was really a very smart way of doing it. And this is how femtosecond laser pulses were generated. But then it was difficult to make even pulses which were even faster. So there was a certain limit for a long time. And the plan for the 6 lectures that I will be delivering here is the following. Some of this you might have heard in earlier lectures. Today in the first and second lecture I will concentrate on the high odd order harmonics which are generated for attosecond pulse generation. Now, what is important over here is that this high harmonic generation, this is collinear with the incident infrared laser. You shine in an infrared laser, what you get out is attosecond pulses of higher frequencies, multiple of the original frequency, 3 omega, 5 omega, 7 omega, and you can go up to many orders, but these are coherent. And what is it that makes them coherent is part of the topic that I will be addressing in the first two lectures, why they are coherent. So, the focus will be on coherence, and I will discuss it in the context of time domain interferometry, which is also a very exciting field. So, we all know that we have come across Feynman's remark that all the essence of quantum mechanics is contained in the Young's double slit experiment, but those double slits are separated in space. So, you have got a physical apparatus in which you have got two slits separated by a small distance. Now, we are going to talk about time domain interferometry in which a wave packet is going to be split in the time domain. So, there will be interference between parts of the wave packet at time t1 with another wave packet, another part at time t2. So, this is really very exciting. So, we will discuss it in this context of time domain interferometry. And then in the next 4 lectures, I will talk about the attosecond time delay in photoionization process. Now, if you look at this experiment which you would have studied in your high school, this is the photoelectric effect. Light shines on a metal plate and electrons are knocked out, and then you can measure the current and intensity and so on. And the explanation of this is what led, it was given more than 100 years ago in 1905 in Einstein's magic year, for which was explicitly referred to in the citation of Einstein's Nobel Prize award. So, Einstein explained this, but he assumed that the photoelectron ejection is instantaneous, and it was a perfectly good approximation more than 100 years ago. Neither the theory nor the experiments were developed at that time to recognize that there may in fact be a small time delay in photoionization, and that is what I will be talking about, and that needs a good bit of quantum collision physics, which is what I will review in the next 4 lectures beginning tomorrow. So, it will be mostly on collision dynamics, in which we will have to visit certain aspects of quantum collision theory. We will visit time reversal symmetry in quantum mechanics, the reciprocity theorem in quantum collision physics, and we will discuss what is it that makes the time delay in photoionization measurable at all. Is it measurable at all, and if at all it is, why is it measurable? So, these are the questions. It is not only in photoionization, which is PI, and PD is photo detachment. Glad to have Arvind over here, who is an expert on these things, especially photo detachment. So, the measurability of the Wigner time delay in photoionization and photo detachment will be the focus of our discussion in the next 4 lectures. The last lecture will be about having an operator which is self adjoint. You know that for any quantity to be an observable, it should be possible to represent it by a Hermitian operator, a self adjoint operator, but there is no such operator for time itself in quantum mechanics, but for time delay there is, and that is what I will talk about in the last lecture, in the 6th lecture. Now, I am sure all of you have seen this picture. Is there anybody here who hasn't? Everybody, because there have been lectures by Shiva and Vinay, and I very much wanted to watch those lectures, but I did not get a chance, Shiva. but I am very sure that this has been shown and discussed. So, this is how attosecond pulses are generated. This is the famous 3-step model of Paul Corkum, and you have an applied laser field. This could be in the infrared, and then what comes out are ultraviolet pulses because of this frequency augmentation by a factor of q. And this is really amazing, because what is happening over here, you have the dotted line which represents the atomic potential. The dashed line is the laser field potential. So, the laser field has got the electric vector, and the electric vector interacts with the electron, and this is similar to what you study in Stark effect spectroscopy. It is exactly the same picture really, and you have the net potential which is influenced by this, but you have to remember that we are talking about ultrafast processes. So, this direction of the laser potential, the laser field, is going to swap in half a cycle, because the sinusoidal wave will go to a maximum, go to 0, and then go to the negative maximum as a sinusoidal field. So, it is going to swap. So, what looks like this is going to look like this in just half a cycle. So, that has important consequences in the phenomena that we are going to discuss. Now, this is an important step, the step number 1 of the 3-step model, which is the tunneling ionization. The incident photon does not have enough energy to effect photoionization in the Einstein sense, okay. But because of the laser field potential, the effective potential is lowered, and it is possible for the electron to escape through tunneling, and this is the same process that you have learnt in your first course in quantum mechanics, which is tunneling through a potential barrier. It is essentially the same phenomenon. You have tunneling ionization which takes place, and then as the direction of the electric field reverses in the next half of the cycle, then you have the wave packet which has escaped. It experiences a force in the opposite direction. It is pulled back toward the parent atom, it recollides with the atom, but during its travel through step number 2, it has gained a lot of kinetic energy, and this kinetic energy would be released when this electron, when and if this electron is reabsorbed. There are complex conditions which are necessary for this to happen, but when this happens, this excess kinetic energy which the electron has gained is released as higher energy photons. So, this is how you get the high harmonic generation. Now, you are really talking about a very short time window. So, here this will happen only when the electric intensity vector of the electric field is almost the maximum. This is a very strongly nonlinear phenomenon. So, if it is anything less than that maximum outside those red lines, okay, you will not have tunneling, okay. So, you can have tunneling only when you suppress it to a certain extent, and this is a very rapidly occurring phenomena, and how coherence is achieved in the emission of this light over here. So, one can understand from the point of view of conservation of energy that the excess energy which the electron has gained during its travel is released, but what is it that makes it coherent? Now, that is a question that we are going to discuss in today's lectures, this one and the one after lunch. So, here the phenomenology involves multiphoton ionization. This is essentially a strong field phenomenon. The atom can absorb number of photons, it swallows a large number of photons all at once. It is like, you know, these eating competitions in which you eat a number of laddus all at once, not just one at a time. And if you want to win, you will swallow multiples of them. And this is the kind of thing that is happening. So, I will come to this relation a little bit later, but one of the earliest breakthroughs in this happened in the early 1980s in experiments done by Anna Wheeler, who is one of the Nobel laureates. And what she observed is that if you have very strong field, means if you look at the conventional interpretation of Einstein's photoelectric effect, you say that okay, nothing is going to happen if you change the intensity of the incident light unless you change the frequency. Now, that is strictly correct, but only within limits. If you go beyond those limits, if you go to extremely high intensities, and that is where we enter the domain of strong fields. So, the intensity is the power is something like 10 to the 15 watts per square centimeter. When you go to extremely high power lasers, then what you get is electrons which are knocked out, as one would expect. You get ions, as one would expect, but there is something about the ions that I will point out which is different from conventional expectation. And then you get something else which was suspected to be noise in the earliest experiments, and it turned out that this was not noise, but this was higher harmonics of the incident radiation, because they did not know that okay, high multiples of frequencies could be generated in this process. So, they thought that this is some sort of noise, and it took the ingenious experiments of Anna Wheeler and her colleagues to discover that there was a systematic in this, and a brilliant one it turned out to be. There is something about the ions which I should point out. The higher harmonics in the first place, the intensity of the higher harmonics drops for the first few harmonics, but then not necessarily, it does not keep dropping. It meets a plateau, and then there are unexpected variations in the intensity of the higher harmonics, which is a very strange phenomenon. The ions also, it is not just a single single ion in the sense an ion which is singly ionized, but you get multiple ions, ion in which 2 electrons are knocked out. And Anna Wheeler, she observed not only singly ionized atoms, but also doubly ionized, even triply ionized, and she also saw quadruply ionized species. So, this was a very strange phenomenon, and this comes under the general category of what is called as non-sequential double ionization. So, let me remind you what we expect from ordinary perturbation theory, and this is an equation which you would have met in your quantum mechanics course, the Fermi's golden rule and the usual time dependent perturbation theory. It gives you the rate equation for transitions in which you have the Dirac delta, and correspondingly you get the probability of single photon ionization, which is a product of the photoionization cross section, photon flux density, and the pulse duration, because it increases with time. You get a rate equation and then it gets scaled by the time. So, the pulse duration scales it, and you have the cross section, you can get it from first order perturbation theory. I will not discuss this, I have dealt with it in my quantum mechanics book. But then what you can consider is, after all these transitions can take place by exploiting the uncertainty between energy and time, and this is again a very peculiar phenomenon in quantum mechanics which needs careful attention. because of the energy time uncertainty, in that time uncertainty, is it possible for the atom to swallow two atoms of the same frequency? If you consider that, then you can have a 2 photon absorption, and this is the model which was invoked. This can happen because of the energy time uncertainty. This is sometimes referred to as the uncertainty relation, but it is not quite the same as the Heisenberg uncertainty relation, because position and momentum are canonically conjugate, energy and time are also canonically conjugate. But if you remember your study of the uncertainty relation for position and momentum, it comes from an analysis of the expectation values of the operators and the root mean square variation and so on, and you define an operator for position as well as for momentum. You have the gradient which comes as an operator for momentum because it is the generator for translations. So, you need operator for position and momentum both. Now, you can't do that with energy time because there is no operator for time in quantum mechanics. So, this uncertainty relation is absolutely valid, but it is not quite the same as the Heisenberg uncertainty principle, and it is strictly speaking, I would call it as the Mandelstam-Tamm relation rather than the Heisenberg relation, but it has got the same form, the same structure and very similar consequences. But this is a very interesting topic for study, but that is not a part for today's discussion. So, this is the photoionization probability for single photon ionization, and then Maria Goeppert-Mayer, who got a Nobel Prize for the nuclear shell model, she studied the 2 photon absorption within the Mandelstam-Tamm uncertainty to swallow 2 photons to get expressions for double ionization, for multiple ionization. So, her study suggested that the probability of 2 photon ionization would be the product of the single photon ionization with another similar factor. So, it will go as the square of this, and since the probability is multiplied, the probabilities lessen. Okay? Every multiple order, the probability, you expect the probability to go down, and this was the expectation. But what was found in the experiments of Anna Leweiler was that the probabilities did not go down in such a simple manner, and it was obviously an indication of the fact that the perturbative treatment breaks down. The perturbation theory does not work at these intensities, at intensities at which Anna Leweiler was carrying out her experiments at 10 to the 15 watts per square centimeter or of that order. This is where you need a different approximation altogether. Perturbation theory does not work, and the approximation that you talk about is the strong field approximation, which I am sure Shiva and Vinay have discussed quite extensively in this course earlier. So, let me just draw your attention to some important papers in this field which are very nice to read. The literature is vast and there are brilliant papers, but I particularly like this paper in the American Journal of Physics, which is a pedagogical paper by Anna Leweiler and her collaborators. I will be sharing these slides, so you do not have to write down everything, but something that you should register. And this is the kind of spectrum that Anna Leweiler observed, and you see that there is a perturbative domain, the intensities drop, then there is something like a plateau, there is also a cutoff, and the important thing is what seemed like noise were high order harmonics which were collinear with the incident laser, they were odd multiples of the driving frequency. Okay. So, this is the systematics which came out of what was initially suspected to be noise, and then it was also found that the intensity of those higher harmonics drops, but not monotonically, and there is also a cutoff. The high order harmonics do not go forever, which is really not surprising because you certainly can't generate infinite energy. So, that is not surprising, and this is the non-perturbative behavior that was seen, and it is not a surprise that the 2 photon ionization cross section is measured in units of GM, named after Mayer, Georgette Mayer, who actually got the Nobel Prize for the nuclear shell model, but she made important contribution to this field before she studied that. So, this is again a picture which shows how the intensities change, and this is the 9th order, 11th order, 13th order, 15th. So, first of all you notice that there are only these odd order multiples of the driving frequency. That is the first important point to register. There are some other peaks that you see which do not quite look like noise. You might suspect, you might wonder what they are, but they are not harmonics. They are second diffracted orders of the 21st, 19th and 17th harmonics respectively. So, one has to do careful experiments and careful analysis to figure out what is what. And then if you look at this intensity distribution, the 3rd harmonic is here, the 5th is here, the 7th is here. Now, it has not gone less than that of the 5th, and then you look at the 9th, 11th and so on, and you see that there is this plateau, and then there is this cutoff over here which was seen at the 21st in this. Although in many experiments you can go to much higher order harmonics, not just 20, you can go up to 100 and several orders of harmonics you can get. This is obviously non-perturbative, and look at this. This is I mentioned that you get ions not just singly ionized, but also doubly ionized, triply ionized and even quadruply ionized. But if you look at the number of ions in certain units, this is in arbitrary units, then this slope changes over here for the second doubly ionized things. And this is what happens when the laser intensity increases. So, once you get into the strong field domain, you get into non-sequential double ionization. So, all these phenomena are related to each other in a very intimate manner, and this is part of the same topic that we are studying, and this is the probability of the double ionization goes well above what is predicted by perturbation theory.